company. They have been extremely successful. They were a startup from UM, right? So they came out of UM many years ago, and they're kind of the leader in carbon dating. Again, a UM story, a Miami story. So it's a very, as you know, we are all very entrepreneurial. So it's great to hear what they're doing. But Dr. Scott has a PhD in physical chemistry from Northwestern, then did a postdoc work at Argonne National Laboratory in Chicago, and she was also a postdoctoral fellow at Columbia University in New York, and then became an assistant professor at UM in chemistry, and then went on to beta analytics. And she's been very successful there as well. In fact, she got a couple of SBIR. These are industry university grants, as you may know. And her work is primarily in, well, right now she manages the dissolved organic carbon and methane hydrocarbon projects. But she's also a specialist in lasers, and that's why I know her. Because whenever our laser comes out, I call her and it's like, Amy, what do you think is happening? And she's always very collegial and very helpful. But today she will give us a talk on evolving methodologies in radiocarbon dating, and I hope you're enjoying the talk. So thank you.
Can you guys hear me in the back okay? Okay. Yes, I have known Jessica for quite a while. In addition to our conversations about ultra-fast lasers, we also have children who have been friends for a long time, so I think that's just an added benefit. So yes, you know, essentially I've been in academia. I spent most of my career in academia, and then 6 years ago I made this massive jump into industry, and it has been very enlightening. I've had SBIR grants, and I thought that I would talk about that today. 2 SBIRs, one that basically panned out into a revenue-generating service, and my team is actually managing that service at the moment, and another project that is a little bit more high risk that essentially is stalled. So I kind of wanted to give you the real sort of how it is in industry. Not everything is perfect, not everything works out, and so that's what you'll see today. So being part of this radiocarbon laboratory, it turns out that the largest radiocarbon lab in the world, and I'll say that because it has been said many times by many other people, is located here in Miami, Florida. And I will show you some of the history from which, and old pictures, essentially how this radiocarbon lab evolved from the University of Miami to what it is today. So, go to the next slide, to the agenda. So I'll go over the radiocarbon dating history just so that we're on the same page. We'll talk about Beta Analytic as formed as an LLC in 1979. They actually started in the ground floor of the Cox Science Building at the University of Miami. They later moved to a lab in Doral, and then to the current location on 72nd Avenue and Bird Road in sort of, I think it's called a Marina District sort of warehouse. There's Lincoln's Beard is there, if you know where that is. So we like to go there after work sometimes. Interestingly, at that time, as they started Beta Analytic for radiocarbon analysis, they formed a sister company called Alpha Analytic, and that is based off of a related geochronology, essentially measuring thermoluminescence, and this is, again, a dating method that's supposed to be complementary. So I'll talk about the instrumentation, the development, improvements in accelerator mass spectrometry, which is essentially what we use now as the golden standard for C14 counting. And then the future, which is the laser-based methods, which is essentially why I was hired. The research and development department started in 2019, so the best way to describe Beta at that time was a 40-year-old startup. So they had quite a bit of cash, they had a lot of experience, but when it came to developing anything new, they were very inexperienced. So that's when I came in, and we've grown to several people at this point. So the two projects that I will talk about is related to the alpha analytics. So thermoluminescence at that time was essentially, can you date any sort of event in quartz or feldspar grains back, let's say 200,000 years. So it's a very cumbersome type of method, and now what people are looking at is optical stimulated luminescence. So that's sort of the more modern version of TL dating. So we basically took what we knew from alpha analytic, and I'll show you some of the old pictures, which are interesting, and we were able to write this into a National Science Foundation Small Business Innovation Research grant. So we got that grant maybe about 4 years ago, and I'm going to walk through some of the things that I did, just because I know some of you might be interested in this SBIR process. So I thought I could share with you exactly how that happened. The second project was actually an EPA SBIR that was tailored to methane emissions testing. And so that was a 6-month grant at $100,000. And so that was like a really nice cash injection into the R&D project. That was around 3 years ago. And so where we are today is we're actually running a service where we're generating revenue. And in the last year and a half, we've made over $500,000 just from this service alone. So I'll talk a little bit about that as well. So let's just go over a little bit about isotopes. If you've taken general chemistry, obviously you've learned about isotopes. But even as a formal chemist by training, we don't really think or talk too much about carbon-14 dating, just because Libby won the Nobel Prize in the 40s, and so we don't really think too much about it in academia. There are a lot of accelerator mass spectrometers that are associated with certain universities. Penn State, UC Irvine, even Yale have an accelerator mass spectrometer now to do carbon-14 dating. But in general, when we think about carbon-14 dating, what we're thinking about is a very, very tiny, tiny parts per quadrillion portion of C14 that is composed of elemental carbon. So elemental carbon on the periodic table, the mass is 12.011. So that means that the vast majority of carbon that exists is carbon 12 and carbon 13. So you can look at those percentages right there. So you need almost a billion molecules or a billion atoms of carbon 12 and carbon 13 before you can detect one carbon 14 atom. So this was sort of nature's gift to us by having this radioactive carbon 14, which decays exponentially with time, and so you can date back 50,000 years. So carbon 14 is actually generated in the upper atmosphere, so we're constantly generating C14 in the atmosphere. Anytime there's a nuclear testing, we will elevate C14 in the atmosphere as well. So in the 1950s, during the bomb testing, we actually elevated quite a bit C14 in the atmosphere. If we think about this in terms of an activity of C14 at that time, it was about 200% carbon in terms of the activity. So we call it a percent modern carbon. Right now we're about at 100 PMC, so that's all decayed. We also are burning fossil fuels, so that is also affecting the amount of C14 in the atmosphere. So this C14 enters the photosynthetic cycle as 14CO2. So us humans, yes, we have radioactive C14 in our bodies. We are eating plants. And as long as we are alive and living, we are incorporating C14 into our bodies. So the moment that we stop eating food, or if there is a death, for example, is when you are now removed from the carbon cycle. And that's, the clock starts for the C14 dating. So you can really only date the moment of a death for a living organism. So this decays back, a half-life of 5,700 years, and then the actual dating back, at least for our laboratory, we date back 43,500 years. And that's where we feel comfortable in terms of dating. You'll see other labs that will say more like 50,000 or sometimes 55,000, but it really depends on their instrument detection. So one of the other interesting things about nature is that carbon isotopes do not incorporate statistically in the photosynthetic cycle or in the ocean. So I'll talk a little bit about how these bond-breaking, bond-making reactions will actually deplete or enrich carbon-12 relative to carbon-13. We use that also as a way of tracking these processes. So this is just another picture, essentially, if you want to see how this works, how we're part of the carbon cycle. We have the cosmic radiation, so I kind of already mentioned. So we have C14 that ultimately gets into the photosynthetic cycle. So we also have CO2, which can dissolve in our oceans. So we have dissolved CO2, carbonate, bicarbonate, dissolved organic carbon, particulate organic carbon. So you can imagine all of the different ways that carbon-14 can be used to understand ocean cycling, movement of carbon in water systems. So there's just a wide variety of projects and interests in carbon. Anything that basically has carbon can be carbon dated. So as I mentioned, that the carbon isotopes do not incorporate statistically. It's our sort of natural tracer. And so we can look at this by looking at the C13 to 12 ratio. So in these measurements, we actually use two major instruments, accelerator mass spectrometer, and then we use a smaller isotope ratio mass spectrometer, and this measures the stable isotopes. And together, we're able to measure carbon-14, carbon-13, and carbon-12. When we do the math and all the sorting, there's actually quite a bit of calculations and sort of assumptions that you make, but with respect to the stable isotopes, which you do need in order to correct your carbon-14, we use these equations. So we're always measuring everything in terms of ratios. That's why it's called an isotope ratio mass spectrometer. So these are the equations, and then essentially what this looks like is that as CO2 from the atmosphere gets incorporated into the photosynthetic cycle, and we can use that delta notation, which we know is the carbon-13 ratio that we measure on our instrument, we can see that we're depleting the carbon-13 relative to the carbon-12. And part of that is because the zero-point energy and any sort of kinetic or thermodynamic reasons as such that carbon-12 would be incorporated first into the photosynthetic cycle. So by the time you measure a C4 plant, you're depleted by -10. That's per mil. If you look back on the equation, it's times 1,000. So they use this, instead of like part per thousand, they use per mil. And then this little like dollar, it's not a percent sign, but it's a per mil. Nevertheless, so we can go through and say, you have all of these different C13 values, and they are used in conjunction with C14. C14 just tells you where in the decay curve you are, but the C13-12 ratio can tell you essentially how that depletion may correspond to a certain process. So later when I talk about methane, we would expect them to be much more depleted than something, let's say, if I was looking at a carbonate material. So all of this is important, and we use a lot of other types of materials. Here we have a reference which is incorporated in this calculation, which is also incorporated in our C14 calculation as well. So we can use this to understand climate of the Earth, carbon in the atmosphere, we can reconstruct history, we can learn how our bodies work. So people can incorporate C14 in drugs and tracers in the body. You can look at metabolites using C14. And those are generally artificial, like artificially elevated C14. The studies that we do are natural abundant, so we don't accept tracers and so forth. So we're not really like focused on those kinds of experiments and studies. But nevertheless, we can go back and think and take a look at some of the measurements that were done. And so here's Libby in 1947, who is talking about methane. And so part of their discovery was that they had to make sure that the radioactivity was coming from carbon. And so one of the ways that they could do this is by taking a fossil methane from oil and gas, and then they can take methane that is from, I believe this is from a Baltimore waste sewage plant that is, producing methane from organic waste. And so they should have different activities. So anything that comes from a living organism or the waste product of organism that was sort of still living or just died should be, if you see, in balance, equilibrium with cosmic radiation, right? So that essentially you're still in the carbon cycle. So there should be a lot of C14 activity for that methane, and then for the methane that is from oil and gas should be completely fossil is what we call. So there's no C14 activity. all the carbon, and carbon-14 has decayed exponentially with time. So the way that they did this was they had to purify, I think it was like 700 liters of gas. I mean, this is like, it's hard for us to conceptually understand this from 1947, but nonetheless, at this time, so they had the methane, they had to combust it, they have the 14 CO2, and then they make calcium carbonate as a solid. So one detail about this experiment is that they were able to say, or to conclude, that hydrogen or tritium or any other elements were not part of that radioactivity. And then you could really see that big difference in here they were doing counting back then, but nevertheless you can see that the biomethane has a much higher count, C14 radiation from the beta electron, than the petroleum methane. So I will revisit this in our project later, because that was the purpose of our SBIR grant, in fact, was methane radiocarbon dating. So Beta Analytic was formed, as I mentioned, in 1979. There were two people involved in this. They were both academics. Murray Tamers was a physical organic chemist, and then he had met Jerry Stipp, who was a geologist. So I think this unique pairing, this combination of sort of the applications in geology, geochronology, and then having that chemistry side really made these two guys successful in starting this company. The radiocarbon lab was originally out of the University of Miami, so they still do have some radiocarbon, but they do not use the more advanced accelerator mass spectrometry like we use. So these are some of the pictures. I actually never met Murray Tamers, and I never met Stipp, but I did meet his son. His son was basically taking over the company. He's the one who started the R&D department, and his son looks exactly like him. So that's fine. I can look at him and say, okay, that's his son. And then this is an old picture. I don't know who that guy is, but this is what the lab looks like, right? It looks like this at that time. I can't show you pictures of what our lab looks like today, but I'll tell you it looks pretty similar to that. Okay, so we do a lot of old-fashioned organic chemistry. We do a lot of cryotropping. We combust everything, we burn everything, we generate that CO2, all that C14 transfers to CO2, right? Libby just showed that experiment with methane. And so that's exactly how we do those experiments today. So in that regard, not much has changed. It's just really the detection of the C14 that has changed. So when Beta first started, they were doing this by, again, the combustion method. And what they were actually doing is liquid scintillation counting. Okay, so you have your, essentially your beta electron. They would actually make benzene, so they would combust and then take that CO2 and make benzene. And then they would have this fluorescent molecule, and that beta electron essentially would excite, transfer the energy, and then you would measure this in a photomultiplier tube. Right? So this was an emission study. That instrument at that time, I don't really know what it costs, but you can buy one now. You can still buy LSC instruments for about $125,000. So you can see the footprint is pretty small, right? At the time, they were doing a lot of measurements. They were a radiocarbon lab. They could get you a C14 date in 30 days. So if you had a bone from a dig, or you had a shell and you wanted to date that, you could send it to Beta Analytic. And when they started, they would call up their friends, and they would say, yeah, send your sample, and then they would never charge them. So I would say that as business people, they were not particularly the greatest in that early time. Just because I think that they were really, in that academic sense, that they wanted to contribute and give and basically take all the sort of things that they've done in order to speed up the C14 dating and give it to their friends and say, yes, your project is important, send your samples in. So now it's completely a commercial enterprise, right? We're not really giving away C14 dates. We do a little bit in the R&D department, so that would be the only case. So that's liquid scintillation counting. I don't have a picture of Beta back in the day, but I heard that they had like 30 of these instruments, and that was just because everybody's sending me samples, and once the sample comes in, it needs to go into an instrument right away, right? So around 2005, National Electrostatic Corporation in Wisconsin had been selling these accelerator mass spectrometers. So this is like your typical mass spectrometry, your You're ionizing the sample, you're generating these charged, in this case, carbon-14 atoms. You're mass sorting them and you're detecting them. So you're doing carbon-14 counting. This is what the instrument looks like, and we have 6 of them. So 6 of these $1.5 million instruments is a lot. It's a lot to manage in terms of facilities. We have 4 buildings, 2 floors for each building, and we just installed our last 2 accelerator mass spectrometers. So we went from 4 to 6 in the past year, just because of the number of samples that we're running every year, which, you know, I think last year maybe was like 30,000 samples or more, which is a lot of samples. So really the lab is now a production lab, right? And that's where the revenue is coming in. So the only difference between this sort of photo is that we actually, the source is over here, so the sample is over here, is that we have 2 sources. And what that means is that we can prepare all the samples, we can have one pumping out, cooking, while the other one is running, and then when this one's done, then we can run these samples. It's just high throughput, this is what we do. So this is the state of the art. If you want the best precision, the best resolution, all of it, accuracy, accelerator mass spectrometry is the golden standard at this point. So I just took a little bit of information about the AMS. This is from NEC. They're really, maybe there's another company, but for the most part, people are purchasing the instruments from NEC. So we use a cesium source, okay, elemental cesium source. So all of our samples, when they're put into the sample wheel, they are composed of graphite. So again, we take the carbon substance, doesn't matter what it is, it could be a shell, it could be methane, it could be a bone that we extract the collagen from, we combust it, we make CO2, we purify the CO2, and then we graphitize. So at the end of the day, we can handle that carbon as graphite pretty easily. We don't have to do a lot of air-free chemistry. So we pack it into a wheel, it goes into the source here, it gets ionized. Then it goes through this flight tube here, and it talks a little bit about, you know, first your negative charge and your positive charge. You're stripping out all these other isobars, obviously, because you have some nitrogen in there, which is going to interfere. Then you go through your magnetic sector, right? And you do have 3 Faraday cups. You do measure carbon-12, carbon-13, carbon-14. But really, the most accurate, precise measurement in this particular case is your carbon-14 measurement. Okay? So we don't really use the carbon-12 and the carbon-13 from the AMS. The newer AMSs claim to have better measurement on the other 2 isotopes. So that's kind of something new for us. Typically, as I mentioned, we use the isotope ratio mass spectrometer. It's a different instrument, and that's how we get the 1213 for carbon. So that's what it looks like. We went through the building process at our company. It was interesting. But let's talk about the future, because not everybody has access to an AMS, and from a company revenue generating perspective, we want everybody to send their samples to us. That's what we want. We want the total market, we want all the money. That's how it is. If somebody's sending their sample elsewhere, why are you not sending it to Beta MSC, right? So to date, we have run over 700,000 C14 samples. Every time a sample comes in, it gets assigned a beta number. We're at 700,000 right now, okay? So we are the leaders in C14 dating. Now, it turns out there are other ways to do C14 counting. We don't have to use mass spec. We can do absorption of 14CO2 itself in the near infrared. So we don't need to make graphite. We can keep the CO2 from the combusted initial sample, and then we can use lasers and just look at the absorption, right? But the absorption is really weak. You know, it's difficult. So here are a few examples. This is NIST. So they actually have been working on a laser-based system, a cavity ring-down spectroscopy. So you fill your gas in this like laser cavity, bounce it like 1 million times, and you do absorption. So it's kind of like a Beer's law. Based on the cross-section of the molecule, you have absorption. And so if you know the absorption, you know the concentration. So here they're talking about advanced optical radiocarbon sensing is under development across the world. You can address challenges in climate change, biomaterials verification, which I'll talk a little bit about, nuclear emissions monitoring. Each application could impact the future of radiocarbon sensing and metrology beyond precision radiometric dating. Okay, so this is really, a lot of people are working on the laser-based method just because the AMS is just such a pain, right? I mean, you have to have a complex facility, you have to well-trained employees, which we do. We have engineers that work on site, and their job is to maintain the accelerator mass spectrometer. We have another group out of Italy. So they've been developing saturated absorption cavity ring down, so just another variant. So there's a lot of these variants. You can often optimize the laser cavity, et cetera, et cetera. And they are now selling a laser-based system for about $500,000. You don't need to make graphite, but you do need quite a bit of CO2 in there. So this is what their company website says. So you take your sample, I kind of mentioned this already, solid liquid gas, anything that has carbon, you have to combust it. You can do this either manually, we do a lot of by hand with a torch, we combust a lot, or you can use a elemental analyzer, you put the solid in and it will combust. And then there's your CO2, and you're gonna measure the absorption directly of the 14 CO2. This is what the instrument looks like. So it's supposed to be like a relatively large tabletop instrument. And then this is one of their diagrams that came from their website that basically just looks at, you look at the laser ring down with the gas and without the gas, okay? And so then you can just tell the absorption there. So it's relatively straightforward, but to do this, in a way where you could just sell the instrument and the user can just pop in the CO2. I think the biggest drawback here is that you need 0.7 liter net volume, although pressure may be low. Dealing with samples like this in a big canister is kind of a pain, right? The sample sizes that we deal with are 1 to 2 milliliters of CO2. So we have every sample in like a little vial. It looks like this, okay? So this is very cumbersome. Now, if you're a huge company, I can't say who, so I have to be careful what I say, and you want this in-house measurement because you're trying to optimize your methane production, let's just say, as an example, and I had enough money and I had enough technical expertise, I could buy this instrument, and let's say I wanted to run 3 samples a day, I could probably handle the 0.7 liters. Okay. So where the technology is now, as far as I know, this is the only commercial laser-based C14 system. Okay, but again, there's like other people working on various aspects of this. So if we look at this progression all the way from liquid simulation counting, where you're looking at the actual beta decay, versus AMS C14 ion counting, first you can see the sample masses are quite different, right? So LSC just requires a lot of sample, but if you have a bone and you don't have a lot of it, or if you're trying to measure a tooth, we get a lot of teeth from various animal parts and animals all over the world. Obviously that could be a problem. So AMS has a lot of advantages. This is why it's the gold standard at this moment. When we talk about the precision or the agreement among the data, we have less than 1%. LSC, I suppose, is about the same. And again, we already talked about some of the advantages for beta, but just having access to a C14 laboratory can be challenging. So the laser ring down spectroscopy of the wide variety that people are working on, different laser colors, different whatever, is based off the CO2 form, so you don't have to graphitize. So when it says elemental carbon, they mean that after you combust, you make that graphite as elemental carbon. You need much more sample, which we kind of already saw. Measurement time is the same, but the precision is not there, so that's a problem. We have a lot of regulatory drivers right now where C14 is required, but you need a certain precision. So that's not going to work. All these laser-based methods are not going to work. So this is really where people in academia, where people, even in companies, are working to try to essentially optimize this laser spectroscopy. So this is a paper I pulled from the group in Italy. So this is their C14 activity. This is 130 PMC or 134 PMC. This is one of our oxalic acid standards. It came from feeds from 1950. So we use this to do corrections. And you can see the SCAR, the laser-based method, the error bars are quite large compared to the accelerator mass spectrometer, right? So if you're going to report a data, if you're going to send data to a regulator, if you need a fast result, you're going to go to beta analytic and you're going to use the AMS and you're going to pay the $600. And that's what's going to happen. So obviously, as a company, where do we fall in here, right? So obviously, we have adopted technology from LSC to AMS. It doesn't look like in the immediate future we're going to adopt the laser-based methods, but we know the people that they're going to be out there. So really what is the future is real-time monitoring using C14 with these laser-based methods. That is really the future here. But you always need, the accelerator mass spectrometer, you need that gold standard to really validate everything. So it's always going to be important. It's always going to be important. And I would say even if you look at the progression of other types of analytical instrumentation, you have advantages in laser-based methods and you have advantages in mass spec. Mass spec will never go away, right? We all have probably used the mass spec here. So there's another side technology that I wanted to mention with the stable isotopes. So this is your carbon-12, your carbon-13, much more abundant. You have much fewer problems that I've been mentioning compared to the C14. So Pucaro started out with a lot of SBIRs, maybe like 15 years ago. They probably, I think it was like several $1 million, and they now sell these box CRDS instruments where basically you can do environmental monitoring, you can measure concentrations of CO2, CO, methane, water vapor. We have one in our lab actually, in the R&D lab. But right now what we're using this instrument for is for water isotopes. So we do a lot of environmental testing. So you can measure simultaneously the hydrogen 2,1 isotope and the oxygen 1816 isotope. The advantage of the laser-based method over the mass spec in this case is that those absorptions are in two different regions. You can have two different lasers, so you can measure it simultaneously. If you were to do this on the mass spec, you would have to first measure the hydrogen isotopes, all the samples, and then reconfigure the system and then measure all the oxygen isotopes. So this is a very clear example of a laser-based system that we have completely moved to in terms of stable isotope testing. They're relatively inexpensive, maybe $125,000, $150,000. You can put the water sample directly in there, it creates a vapor, it goes into that laser cavity. The Pucaro system, actually, they use a 3-meter system, slightly different than the other version that we saw. So again, you can have a lot of these variants and you can try to optimize this and so forth. But it's a really good system. So now that we've talked about radiocarbon, let's quickly talk about the quartz grain feldspar dating that I mentioned, which was the earlier sister company, Alpha Analytic. These are some of the old product sheets that I found for Alpha Analytic. This started in the early 80s. So they would talk about essentially thermoluminescence. Whenever you have samples that don't have carbon and you want to date them, you can use this kind of method. And this essentially says that when these sediments, sand, quartz, when they're forming, they essentially have inclusions of radioactive elements, potassium, uranium, thorium. And when those sediments, when those quartz crystals are exposed to light, they essentially, let me see this again. So the ionizing elements will ionize and create charge carriers in the crystal lattice. Okay, so over time, as it is sitting there, it will create these charge carriers. When the sample is exposed to light, it will deplete those charge carriers. Now, if that quartz sediment gets buried and gets buried longer, it will not see the light, it will not reset. So what this measurement tells you is the last time the quartz or feldspar sediment saw light, saw sunlight. So if you are looking at Greenland and you're looking at snow coverage, most likely those quartz sediments, feldspar, are not going to see light for maybe 100,000 years. So the longer that the sediment is buried deep, the more charge carriers that you generate, depending on the crystal lattice, of course. So your signal actually amplifies back in time. So for the thermoluminescence and the optical stimulated luminescence, basically the same kind of measurement, similar measurement, you can measure back 400,000 years in time, okay? So another example, you have a burial site, you have bones, you can measure the C14 back 50,000 years, but maybe you're curious if that structure, if there is quartz or feldspar in that building material, maybe some sort of shrine or something like that, you can date the quartz and the feldspar in that material and say, did these two events happen together, or was this built before? Now, of course, you have a limitation with C14 because you can obviously date much further back with the quartz feldspar. So it was interesting, to kind of pull this information. this is what it looks like. So after so one of the things is that I mentioned is that sunlight will deplete your charge carriers and you no longer have your clock for when that sediment was buried. So you have to collect everything in the dark. So you have to pour, you have to take it in the dark, and you cannot have a lot of room lights. You have to kind of work in a photography type of situation. Okay, so once you deplete those charges, so you take it to the lab in your dim room setting, you hit it with the laser and you get all those charge carriers out as an emission signal, right? So we have that signal. But now, in order to make the calibration curve, we have to redose that crystal lattice with ionizing radiation, and you do this incrementally. You dose it, read the luminescence, dose it, read the luminescence, dose it, read it, the luminescence, and you get a calibration curve. So you can kind of see on the picture here. And then once you get a certain saturation point, and you have a dose rate, so per age, then essentially you can you just divide the two values, and then you can get your age. So this is an interesting old photo that I found from Alpha Analytic. Now again, they were doing thermoluminescence. They're heating the sample. Now we're using LEDs and lasers to excite the sample, essentially to dump those charge carriers with a pulse of light. So here I just wanted to talk a little bit about my history. I think Jessica gave a really good introduction, so I don't really need to say too more, except that obviously my background is in lasers. I worked on femtosecond lasers, and this is kind of when I was hired, that, you know, essentially the lab was incorporating more of these laser-based systems. I showed you the Picaro. So that was a brand new system when I started in 2019, and we have since bought 2 more of the laser-based systems. I constantly evaluate various laser-based methods for C14, although we're not adopting that technology. But these are kind of the experiments I used to do, which were 2-pulse experiments, and I was just taking excited state absorption spectra of any sort of process. I was looking at charge carriers, I was looking at triplet states, I was looking at all sorts of these photochemical reactions on a very fast time scale. We were also developing different materials. We had some solar energy work, other kinds of perovskite work as well. So it kind of fit in with everything that was happening. And so when I started is when I received information about this optical stimulated luminescence. So we had been doing, the company had been doing a customer discovery for 5 years prior to my arrival about this OSL technique. Kind of going back to Alpha Analytic in the 80s, right? Can we resurrect this? People are still interested. How this came about is because when we send out a carbon-14 date, we don't always know what the client's project is. Sometimes they tell us, sometimes they don't. The problem that came about to us is that they would say, our C14 date says 10,000 years, but our OSL date says 20,000 years. And so then we have to rectify the geochronology with respect to C14 and OSL. And it became too hard not to notice all the people that are asking us for the OSL experiment. And it's like, well, we might as well just go back to what we used to do. What can we learn from this? How can we improve over what was happening in the 80s? So that's kind of where we were. So this is a little bit more on the OSL. I kind of explained it, but again, we're looking at quartz feldspar. So we got this grant. Essentially, the grant was like, can we look at different signals from quartz and feldspar? I didn't believe that there was much literature on it. People were just kind of like, testing these samples. They would look at the emission, and they would say, oh, it's like 300,000 years, 200,000 years. But really, I didn't feel like a lot of the fundamental work was there. But this is essentially what I explained to you. So you have to take the core, right? You have to do this in the dark, so you see all the tarps and so forth. And then there's a lot of applications. So again, anything related to events back in time, it could be volcanic activity, any kind of like earthquake activity, and you might see a rift here, right? So if there's like a rift here, you could date certain parts of the core and get information there. So the 2 instruments that were that you could essentially buy to do this luminescence dating was an old company out of the Danish Technical University in Denmark. They're called Riso, and they're actually part of a university. They build an instrument and they sell it. And then the new company was Freiburg, and they also came out of a university in Germany. And so these were basically the 2 options. So in the early years, Alpha Analytic, they could run about 30 samples a month. They had 4 instruments. That was the earliest commercial lab. Now you can do this optical stimulated luminescence. And one of the problems that we learned early on is that the outer core, or the outside of the quartz feldspar grains, have to be eliminated using hydrofluoric acid, and you cannot do this in the light. So you have to do this under like a red-orange light. So that actually proved to be a little bit of a problem. So here's our commercialization plan for the grant. So this is a grant, again, from the NSF that we got, and this is what I propose, that we're gonna try to reduce sample pretreatment. We're gonna look at new near-infrared signals that are coming from the quartz and the feldspar, just because people have not really looked at this in a time-resolved way. Could we use time-resolved laser methods to look at this? And so here we are in our growth. Obviously, we need money from somebody because we're in the negative. And then we're going to develop an analytical testing service. Maybe we can create an online database. We have some intellectual property. And then if we want to develop any further instrumentation, we would need to find a partner. Okay? So this is how I framed it. And then based on the same business model that Beta Analytic has, is the number of samples per year. Could the market reach $5 million? Perhaps, if there are that many samples. There are a lot of samples, actually. There's a huge study in Greenland and so forth. So this is what it looked like. And then the next step was actually to do customer discovery. So when you get this Small Business Innovation Research Grant, they're going to say, okay, you have an idea. You think you're going to look at new near-infrared signals using lasers. Now I want you to go and talk to everybody who's associated with this project and really figure out if that's what people want. Are they going to buy this? What are you selling? Right? So I had to sort of figure all of this out. So we do this so we had a boot camp. So if you ever apply for an NSF SBIR and they tell you that you can allocate $10,000 for a boot camp, say yes, because if you say no, they're going to come back to you and say, well, it doesn't seem like you really know your client base and your customer base. And even if you try to convince them, I do know, I know they want to buy this laser, I know they want to buy this service, NSF will still come back to you and say, are you sure? So say yes to the boot camp. For the EPA grant, also say yes to it's a technical and business supporting TABA is what it's called. Say yes to the TABA. The reviewers will tell you, well, it's like a red flag, right? And they're going to say, oh, well, you guys think you know everything, then why are you asking us for money? You need the support, so say yes. And so we completed interviews. So this is our team. This is our R&D team. I have a geologist on my team. He has a PG, a professional geology license here in the state of Florida. He's worked with me for the last 4 years. He's critical to everything that we do. I wouldn't have learned anything without him in terms of the applications, because at the end of the day, I'm still a chemist. I have a chemical engineer and a zoologist. Okay, so we have a very diverse team, and I personally like that. I learned something new from them, and I remind them of their organic chemistry that they took when they were in undergrad. So we did these interviews and so forth, and then we decided to go to Denmark and go to Riso and for them to teach us how to do this. So we spent 2 weeks there. So they gave us sediments from Greenland, and I don't know who the client was, who they were doing it for, but myself and the geologist, Sean, we were preparing their samples for them. I don't know who they are. So you have to do a density separation of the quartz and feldspar, so we were doing that there. And then here I was loading the quartz grains on their little wheel for the Riso instrument. And here's a few more. This is what their instrument looks like. Here we're doing other types of washing. So there's a very intensive chemical pretreatment. You wash with hydrochloric acid, you get rid of carbonates. You have to use peroxide to get rid of organics, and then you have to do the outermost shell etching with hydrofluoric acid, followed by another hydrochloric acid. So basically, we deconstructed what they do at Riso to figure out how can we, one thing is the actual laser measurement, the other thing is the sample retreatment, which is like really painful, right? We would come out of this lab and I'd be like really delirious with like the color, and it's like, so really like, it's not like a great working condition. So when you're thinking about your laboratory, your production laboratory at Beta, you have people that work there for like 30 years, are they gonna do that for 30 years in the lab? You know, so it's not like super ideal for us actually. And this is actually what some of the samples look like up close. So it was pretty cool to do that. So as I mentioned, what's our pivot? Well, one thing was the customer discovery, and then the other thing was like the samples are really pain to process. And our facility is just not ready for HF. We just can't handle HF, and from a liability perspective, as a small business, it was just too much. So we had another project, and we were essentially using potassium hydroxide, so very concentrated KOH, and we were etching some quartz, and you can do that if you elevate the temperature, and so forth. We only need to etch a little bit of the quartz grains based on what we learned at Rezo. So we basically said our pivot was, can we use other methods or chemicals to safely etch the outermost layer of the quartz grains. So we completely pivoted, and then we started with KOH, and we would heat up these quartz grains. So we actually got samples from Rezo, and so we would start the etching. We thought if we can improve the etching process, we might be able to improve the whole measurement for everybody, including ourselves. And this could be really transformative to really get rid of HF. So that really ended up being the problem for us. It was a problem for other people. They would go to Rezo. Rezo kind of set up this lab inside their university just because people could not use HF in the dark in their institution. So that was a real eye-opener, right? I would have never known this when I wrote the grant. Luckily, these granting organizations do expect some sort of a pivot. They do expect you to figure out what is happening in the field, and they do expect you to find other problems that may be more of a priority than, for example, the laser-based detection method. So that's kind of where that ended. So we're really stagnant. This stopped. Project stopped. And that's how it happens. Sometimes someone comes down and says, okay, you're not working on that anymore, and that was it. We have been purchased by a very large company called SGS, and so we are reselling OSL to SGS now. And we're saying, hey, look at all this that we can do. Hey, maybe we can come up with this green chemical method of etching quartz that maybe, you know, we can basically get back into the game with the OSL. I think it would be very complementary still to carbon-14 dating. I think that's what we see in the business side, again, with our clients. So if we listen to our clients, what are our customers telling us? They're saying they're trying to resolve all of these geochronologies, okay? And there's not that much OSL in the United States. There's a lot of OSL in Europe, right? The two companies that basically build the instruments and sell them are all in Europe, okay? So I hope we can revisit it, but right now the decision is a bit out of my hand. So we just have a few minutes. I just wanted to just touch upon methane testing. So I'm not going to go through all the slides, but essentially, you know, methane is a greenhouse gas. It's part of natural gas, so oil and gas. Methane is coming up. We use it if you have a stove in your house that is natural gas. You're essentially using fossil methane. So EPA obviously is concerned about the emissions testing. The current methane concentration is 1.9 ppm. It's really low. You can measure it with one of those Picaro cavity ring down spectrometers. So you can take it out into the field and measure methane concentrations. You can measure if there's like a plume of methane coming from a landfill, or if there's an oil and gas leak, you can measure that. But you can't source, you can't determine if you do measure elevated methane, is it coming from the landfill or is it coming from oil and gas? Nobody knows, right? Sure, you can try to trace it, right? High resolution measurements all the way down to the point source, but maybe that's not good enough. So carbon-14 is really great because anything that's fossil, oil and gas, is going to have no C14 activity, okay? So we can do a C14 measurement. Something coming from a landfill or dairy digesters or cows or whatever is going to have elevated C14. So it's a really great measurement to differentiate different methane sources. And that's how we use carbon-14. So we got the grant, and I'm just going to go through a little bit, and then we can end. So again, going back to that CO2 cycle in the atmosphere, all the grass here, the cow eats the grass, and then they emit methane, right? So it should be on the order of 100 PMC, which is what we are now, and fossil is less than 0.44 PMC. That's what we measure in our lab right now. And then landfills are kind of interesting. Landfills may have old carbon from the 1950 nuclear testing. So landfills, particularly if you tested landfills in the 90s, you would see very high methane and CO2 carbon-14 measurements. You would see maybe 130 PMC, whereas the atmosphere is maybe like 100. So that's coming from all that plant matter that was thrown into the landfill that is decaying over time. Right now we are measuring elevated levels. We measured West Palm Beach, we've measured Fort Lauderdale. We're measuring about 106 PMC. Again, still elevated from what our 14 CO2 in the atmosphere is currently measuring. So again, that just shows what I showed you before. A little bit about the lab process. So we do use a catalyst here. We make our 14 CO2. We use a cobalt catalyst and we make graphite. So there I just wanted to show you what that looks like. Some of the equations, etc., how we do the correction calculation. And then this is a service that we developed. So a client says to us, I have a dairy digester. I need to verify for the EPA regulatory that this came from a biological source. I need to use your C14 testing. And that's what is stated right now in law. So they send us a sample. We first analyze it and we make sure that there's methane in their gas sample, right? Maybe there's a lot of air. We can't really test air. We need some sort of carbon-containing substance. So that's part of our service. So we built up a whole lab full of gas chromatography instruments. We also have USGS standards, so that is composed of methane, ethane, and propane. They can use these measurements in fracking when they're looking at oil and gas and so forth. You can do C14, you can do concentration measurements. So we actually added this service at Beta Analytic, which historically there were no gas chromatography instruments until we started this service. So we can measure all the different components of gases. Right now, everything that's coming to us, I buy these from Sigma Aldrich, everything is fossil. They don't know it's, they know it's fossil, it's coming from oil and gas, but we confirmed it using C14. So everything that I'm buying, that I'm testing with all of this service, all the intellectual property that I'm not showing you, because it did take 5 years of my life, everything is basically fossil. So again, if we look at that % modern carbon, the activity, I kind of skip because everything is fossil. All of my propanes, my methanes, everything's fossil. And then I get a landfill gas and I'm at like 105 or 106 PMC. And then I have an analytical standard and we're at like 132 or 134, which is what I showed you in the SCAR example. So this is our service. So we actually went to a landfill, we collected gas because we want to understand what our clients are doing. Just like the Riso Denmark example, we're like, okay, how are people doing this, right? It really was insightful. I read so much about landfills. I feel like I know a lot of chemistry about landfills. It's very complicated. Anyways, you have microbes, just like in cows, archaea, that chew up organic matter and spit out methane. Same thing happens in landfills. You get a lot of methane, you get a lot of CO2. If you can collect that methane from a landfill, purify it, upgrade it, you can sell it on the methane marketplace and get a tax credit. So right now in the lab, we have hundreds of samples right now sending to us for methane testing. The past year, they thought that the EPA regulation would go away, but it did not. So everybody waited till Q4 to send us their methane samples. So this is what I've been doing in the last few weeks, managing. So R&D is managing the transition from basically the inception of this project to collecting samples, figuring out all the science, all the infrastructure, the lab. We had a 4th gas chromatography installation, all the way to production, and then we're handing this off to production very slowly. So we hired 2 more people in the last month to help us run production on this methane testing. There's a lot of other regulations too. Propane in Canada has a regulation, and then the EU has a lot of regulations for methane as well. We have a lot of regulatory drivers. We do show our data. We're actually preparing a paper for waste management. I've never published in waste management, but we're going to do it because I think it's important for those readers to understand how you can use C14 to look at methane and CO2 from landfill. And what we're doing is highlighting our scientific capability to use GCs, a prep scale method to separate CO2 and methane, and we collect it out of the GC. It's kind of a strange experiment, but it works out. Again, I spent 5 years on this. And then this is all of our data. So we kind of go through the math, which is always kind of interesting. And then we get the report. So this is what our clients get. they get the report, they say, okay, their methane is fossil, and then they get their C13 value, which I told you before is pretty depleted. So we kind of estimated that from the graph I showed you before. So that's really the conclusion, right? The conclusion is that we're making a lot of money, and that's good because I need to eat, right? No, I like doing science too. I like my group, and I like being like half in the lab, half out, right? And that's really important to me. But what I would say is that when I took that huge leap from academia to industry, it was very scary. I mean, maybe I didn't appear very scared to Jessica, but you know, she was like very supportive and so forth. Nevertheless, a few colleagues at the University of Miami were like, "You're not really going to industry, are you? Like, really?" Yes. But I would say when I talked to my advisor, he said, focus on solving problems important to society and bring to bear any and all subfields of chemistry and other scientific fields, engineering, needed to solve the problems. And then, of course, shed work. I mean, you probably don't know these people, but take the new opportunity and don't look back. And then I would just say that the only way that I've been successful is adopting a growth mentality, particularly in times of uncertainty, right? And this will lead to a more fulfilling scientific career in life. So that's what I will impart from you. And the last little bit is that with this parent company, I just wanted to say that we are hiring. This is the website, SGS. We have labs all over North America. We have the Miami lab, we have the Orlando lab. And then I just did a quick search of our North America. So laboratory testing, they have 121 positions. So hire at all levels. And then these were just the first few that came up. A biologist, a supervisor, an analyst. And so with that, I want to thank you for your time.
Just a couple of questions. There are urgent questions. Oh, sorry.
It's okay.
Let's have the professor go first.
No, it's okay. You go. No. The students go first. Now, in our department, the students go first.
No, the student goes first.
Yeah. Curious to know one thing. So there is an instrument or methodologies to detect the radiocarbon from the atmospheric carbon dioxide. So in the atmosphere, there are some percentage of carbon monoxide as well. So I think it contains the carbon, the radiocarbon as well. So we need to detect this as well. So with this same setup, can we detect this radiocarbon from the carbon monoxide that we are doing for carbon dioxide?
That's a very good question. I was not expecting that. So carbon monoxide, the way that we process the samples when we burn it out, the idea, so there's a few ways. Some of them we use catalysts, so we try to really quantitatively convert all of the starting material to CO2. Now, it's not always going to be 100%, there's going to be carbon monoxide, or if we take an atmospheric sample, there's going to be carbon monoxide, as you mentioned. So when we do the purification, we actually eliminate carbon monoxide from the sample. So it gets passed through to the pump and into our exhaust, and we only retain the CO2 part of it, whether it's a combustion product. Now, if you're talking about, let's say, a gas sample like the CO2, CO, methane, in one of our gas chromatography methods, we have a method to separate CO, CO2, methane, ethylene, acetylene, all the way to C5 and all isomers. So, yes, we can do that. So if you have a CO sample, we can measure it. We do have people that are interested in measuring CO. We had a few inquiries, and so when I developed, we have names for all of our instruments. We have Lucy and Ethel, and then Johnny Torch and Charizard, because they have flames. So Ethel, we developed, we have a column set that will separate the CO and the CO2. So we would use Ethel for your question.
Yes, I'm Konstantinos in chemistry, Cavalleratos.
Oh.
So I'm visiting the seminar.
Oh,
So
great.
in chemistry, the students ask first the question. So, but anyhow, so you mentioned that SMS, like AMS, is going nowhere, of course, because it's precise. But the huge advantage of optical methods is portability. So I was wondering if any of these companies that develop instruments have reached a point where they have a portable in-field instrument.
So the only commercial C14 laser-based method is the PPQ. And so that is, I mean, if you want to take a huge table like this and make it portable, maybe you could put in a little shed or a trailer and like wheel it around. Yes, you could do that. The only like real portable that I can carry is for the C13-12 12 for the stable isotopes. That one, NASA has a project, they put it in an airplane and they've been flying over the Everglades and Big Cypress National Preserve, and they're trying to look at CO2 and methane flux. It's called the Blue Flux Project. You can read about it online. So stable isotopes, yes. C14, I would say it would require more effort because the instrument is pretty big, right? It's like in a big laser table, like 4x6 or something, probably like that. That's a good question. But that is the future. That is the future. Exactly what you just described.
Any other questions?
Yes.
For you personally, was there a big change in philosophy going from academia to academia?
So the mission of academia is to train students, right? To do fundamental research. You guys don't really talk about money in that sense. So I would say that in the sense when I was faculty, I did think of students as sort of customers. I thought when I'm teaching a class of 200 people at the University of Miami that, you know, they're paying a lot of tuition and I should answer their emails within 24 hours and I should have a lot of office hours. So I guess on some level I had that understanding that in order for UM and universities to thrive, like there was that student involvement and, you know, there is money associated, there is money transacted, okay? Even if we don't really think about it too much. But in the company, I think it comes down to the role that I play. I am the only PhD chemist on site, so I do actually a lot of teaching in the company. So if they ask, oh, can you submit the sample, and they don't know how to do the general chemistry calculation, I give them the answer in Gen Chem style. So I do a lot of that. So in that respect, not much has changed. I feel that my group is very much learning from me in an academic sense because they're not experts in chemistry. I have a geologist and a zoologist and a chemical engineer who's great. They're all great, but they don't remember everything and I have to show them how to pipette sometimes, especially for the water chemistry. So there are a lot of similarities in that respect, but at the end of the day, we still have to make money. The company has to make money. R&D departments don't usually make money. It's unusual for an R&D department to actually run a service and make money. So we're kind of in that transition right now, but we're gonna move ourselves out into a new project, and that's kind of where we are going. So we will go back to the R&D mindset. Right now, I'm kind of in the money mindset. So if that answers your question.
Although also in academia, I think a lot about money. We have to get grants constantly.
Yeah, you do.
I wish it was more.
But the money it's just a different way. So in a small business, when I have no approval process. If I want to order something, I have a credit card with $25,000 and I just order it. So I would say that the red tape is, that I was so happy when that happened. And it's been like that for 5 years, so I can order for the most part what I want. I would say that they do listen to me. We do have higher ups that will have to approve an order that's a capital expense. I would say for the most part that they do agree with what I state, and I will say that the SBIR did help that sort of money aspect, is that R&D is not just like taking all the money from the company and we're not producing anything. So the grant was actually really nice for us. Is it necessary? I mean, no, we are a small business and we do have liabilities. We have our own safety department, which I also head. So I would say that, you know, expenses are a lot when you're in the private sector. You don't have the umbrella of the university to support you in those ways. You know, paying code lights and the exterminator and, you know, painting the hallways and stuff like that, which we all take for granted here at the university. We have to pay for that, for everything, and often manage our own facilities. So, a good question.
That's it. We went way ahead of time. So if you have any question, you want to come down.
Yeah, this is hard.
Let's start with our cards. Right? Thank you again.
I know. It's amazing.